In September of 2025, a peer-reviewed paper appeared in the journal Nature. It described a rock on Mars, roughly 3 feet across and 2 feet wide, shaped something like an arrowhead, collected by the Perseverance rover from a site called Cheyava Falls, inside Jezero crater. The paper described what the rover's instruments found inside that rock: specific minerals arranged in concentric patterns alongside organic carbon, at levels the mission had not encountered anywhere else in 3 years of driving. And then it included a sentence that, if you have been following Mars science for any length of time, stops you cold. The authors wrote that there was no particularly strong evidence for any abiotic explanation. Not biological, abiotic, meaning non-living, and meaning that when the scientists who published this work in one of the most rigorous journals on Earth looked at everything their instruments returned, they could not find a convincing, natural, non-living process that accounted for what they were seeing. Most people, if you ask them, will tell you that Mars headlines follow a familiar arc. Something gets announced, the coverage spikes for 48 hours, and then a quieter follow-up explains that it was volcanic chemistry, or instrument contamination, or a mineral that looks like something biological, but is not. That is the pattern. It has repeated often enough that a certain healthy skepticism has become the default response to anything that sounds like life on Mars, and that skepticism is not unreasonable. It is, in fact, what science asks of us. But this paper is different, and the difference is not in the press release. It is in the specific language of the findings, in the fact that NASA's acting administrator said this was the closest we have ever come, and in the fact that the question the paper leaves open is not whether the instruments worked correctly. The question it leaves open is something older and larger than any single mission: whether we are alone. That question, which has lived for most of human history in philosophy and religion and science fiction, is now being addressed by instruments in active operation on another planet. And the honest answer, as of this recording, is that we do not yet know. If you enjoy documentaries that challenge what you think you know and reveal the deeper story behind the biggest questions in space, do me a favor and hit that like button and subscribe. It helps more than you know, and I genuinely appreciate every single one of you who supports this channel. Now, settle in and get yourself comfortable. Let's begin. To understand what makes Cheyava Falls different from every Mars claim that came before it, you need to understand what Perseverance had been doing for the 3 years before it ever got close to that rock, when the rover landed in Jezero crater in February of 2021. The scientific team had a specific reason for choosing that location. Jezero is not a random patch of Martian surface. It is an ancient lake basin, roughly 45 kilometers across, fed billions of years ago by rivers that carved channels into the crater rim and deposited sediment on the floor below. The expectation was that somewhere inside Jezero, the rover would find the kind of rock that forms when water carries fine particles of sand and silt and clay and lays them down in slow, quiet layers over long stretches of time. Sedimentary rock, the kind of rock that, on Earth, does something remarkable. When you think about how we know anything at all about ancient life on this planet, the answer almost always comes down to sedimentary rock. Clay and silt are nature's filing cabinets. When fine particles settle out of water and slowly compact into stone over millions of years, they trap whatever was present in that water at the time. Organic molecules, chemical signatures, the physical outlines of cells and shells and structures. They lock those things in and hold them. The deeper you go into the layers, the further back in time you reach, and the record just sits there, preserved, awaiting for something with the right instruments to come along and read it. That is why paleontologists spend careers at canyon walls and river outcrops. The rock is not just rock. It is an archive, and crucially, that archive only forms in certain environments, under certain conditions, from certain materials. You cannot read it from igneous rock, the kind that forms when magma cools. Igneous rock is geologically honest but biologically silent. It does not trap organic material. It does not preserve chemical patterns. It tells you about heat and pressure and the interior of a planet, but it will not tell you whether anything was ever alive. For 3 years, Perseverance drove across Jezero and found mostly igneous rock. The crater floor, it turned out, was dominated by volcanic material. It's the kind of surface that formed when ancient lava flooded the basin and hardened. The team found minerals of interest. They found geological complexity. But the sedimentary archive they had come looking for was not presenting itself. 3 years of driving, hundreds of sample cores, and the filing cabinets were either buried too deep or simply not where the models had predicted. That is a long time to wait when you are operating a rover with a finite number of sample collection tubes and a mission clock that does not pause. And then the rover reached the edge of what had once been a river. Neretva Vallis is an ancient channel cut into the western rim of Jezero, roughly 400 meters wide, carved by water that no longer flows. Standing at the rim of that channel and looking across it, you are looking at a gap roughly the length of 4 football fields placed end to end, and every meter of it was sculpted by a river that has been dry for more than 3 billion years. Below the ancient riverbank, the rock changed. The formation is called Bright Angel, and it is what the team had been looking for. Sedimentary layers, clay-rich material deposited by water, compacted over geological time into the kind of stone that traps and preserves. After 3 years of igneous silence, the filing cabinets had finally appeared. Cheyava Falls was the first major sample target inside Bright Angel. The rock itself is roughly 3 feet across and 2 feet wide, shaped like an arrowhead, and it carries something visible on its surface before any instrument even touches it. Here, across the face of the rock, are irregular patches of reddish and whitish discoloration arranged in a pattern that the scientific team described as resembling leopard spots. The visual name is casual, almost playful, but it matters because it anchors something abstract in something the human brain can hold onto. These are not uniform stains or broad color gradients. They are discrete, irregular patches, distributed across the rock face, and each one turns out to correspond to something specific happening in the chemistry beneath the surface. When Perseverance deployed its instruments on Cheyava Falls, 2 of them produced results that, taken together, form the core of the Nature paper. The first is called Sherlock, and it uses a laser to probe for organic compounds. They're carbon-based molecules that are the chemical building blocks of biology as we know it. Sherlock had been scanning rocks across Jezero for 3 years. At Cheyava Falls, it returned the strongest organic carbon signal the instrument had detected anywhere on the entire mission. Not elevated, not notable, the strongest. The sample from this rock is called Sapphire Canyon, and its organic carbon concentration represents the upper end of everything Perseverance had measured in any rock, anywhere, across 3 years of active collection. The second instrument is called Pixel, and it maps the precise mineralogy of a surface at very fine scale, identifying what minerals are present and where they sit in relation to each other. What Pixel found inside Cheyava Falls, in those leopard spot regions, as were 2 specific minerals arranged in a very specific way. The first is called Vivianite. The second is called Greyite, and these are not common background minerals that you would expect to find scattered randomly through sedimentary rock on a planet that once had water. On Earth, Greyite is a mineral that certain microbes produce as part of their metabolic activity. Vivianite forms in the presence of decaying organic matter, and these 2 minerals at Cheyava Falls were not distributed randomly through the rock. They were arranged in concentric reaction fronts, rings of mineral change radiating outward through the clay matrix, in patterns that preserve the geometry of whatever process created them. The combination of Vivianite and Greyite in those specific spatial arrangements inside clay sediment, alongside the highest organic carbon signal the mission had ever recorded, is a combination that on Earth is primarily associated with biological processes. Not always biological, not exclusively biological, but primarily. And when the authors of the Nature paper looked for an abiotic process, a non-living chemical explanation that would produce this specific combination of features in this specific arrangement, they could not find one that held. That is where the NASA COLD scale becomes relevant. COLD stands for Confidence of Life Detection, and it is a framework with 7 benchmarks designed to evaluate how strong the evidence for biology actually is at any given site. It exists precisely because science has learned, through hard experience, to be careful about this question. Yet Cheyava Falls became the first result in decades to register on that scale. Not at the top, not as confirmation, but as a result that the framework itself recognized as meaningful enough to warrant a benchmark. Joel Hurowitz, the lead author of the Nature paper and a planetary scientist at Stony Brook University, described the findings in terms that were careful but clear. He said the data were consistent with a biological explanation and that the team had worked hard to rule out abiotic alternatives. Katie Stack Morgan, the project scientist for the Perseverance mission, echoed that framing, noting that the combination of features was exactly what the mission had been designed to look for, and that what they found at Cheyava Falls was the kind of evidence that demands continued investigation. And let us be clear about what this is and what it is not. This is not confirmed life on Mars. No one at NASA, no author of the Nature paper, and no serious scientist involved in this work has claimed that life has been discovered. What has been claimed is that a specific combination of physical and chemical evidence found inside a single rock, collected from a sedimentary formation in an ancient lake basin on another planet, does not have a satisfying, non-biological explanation. That is a precise and limited claim, but it is not a small one. And yet, the history of Mars science carries a particular weight here, because the history of Mars science is also a history of moments that looked like this one and turned out not to be. Scientists have been fooled before, not through carelessness or wishful thinking, but through the genuine difficulty of reading ancient chemistry in rocks that formed on a planet we can only touch with instruments we built millions of miles away. The question of whether this time is different is not rhetorical. It is the actual scientific question, and the people who found this evidence are asking it just as seriously as anyone listening to these words. And Mars is not the only place whispering. While Perseverance was drilling into Cheyava Falls, a telescope orbiting 1 million miles from Earth was staring at a planet 124 light-years away. And what it found there might be even more extraordinary. The telescope in question is the James Webb Space Telescope, launched on Christmas Day of 2021 and now stationed at a point called L2, at a gravitational balancing spot roughly 1 million miles behind the Earth in the direction away from the Sun. From that position, it can look outward into deep space without the Earth or Moon interrupting its view. And in April of 2024, the scientists operating it pointed it at a planet that, until very recently, most astronomers would not have considered worth discussing in the context of life. The planet's name is K2-18b, which sounds less like a world and more like a license plate, the kind of alphanumeric string you might see on the back of a car in a parking garage and immediately forget. And that is not accidental. When you are cataloguing thousands of planetary candidates discovered by a space telescope named Kepler, you do not have the luxury of poetic naming. You get a designation, a reference number, and a label that tells you which survey found it and in which batch it appeared. K2-18b was discovered in 2015, and for a long time it was exactly that, a label, a data point in a growing ledger of exoplanets that the Kepler mission accumulated over its years of operation. But the label is deeply misleading because what it refers to is something genuinely strange. K2-18b orbits a red dwarf star in the constellation Leo, 124 light-years from the room you are sitting in right now. It has 8.5 times the mass of Earth and a diameter roughly 2.5 times larger. It sits in a category of planet that does not cleanly match anything in our own solar system. Too large to be a rocky terrestrial world like Earth or Mars, but far too small to be a gas giant like Jupiter or Neptune. One working description of what it might be is a Hycean world, a term built from hydrogen and ocean, meaning a planet wrapped in a thick, hydrogen-rich atmosphere sitting above a global liquid water ocean. That is the hypothesis. Whether it is correct is precisely what the telescope was trying to determine. In 2019, the Hubble Space Telescope had detected water vapor in K2-18b's atmosphere. That was already worth paying attention to. Then, in 2023, the James Webb Space Telescope conducted its first analysis of the planet's atmospheric chemistry, led by Niku Madhusudan at Cambridge University, and found methane and carbon dioxide together with a notable absence of ammonia, a chemical combination that, under the Hycean world model, is consistent with the presence of a liquid water ocean beneath the atmosphere. as that finding was already being discussed carefully in planetary science circles when the same analysis returned a tentative detection of something else: dimethyl sulfide. Dimethyl sulfide is a molecule you already know, even if you have never heard its chemical name. It is the molecule responsible for that distinctive smell of the seaside, that sharp, briny, faintly sulfurous scent that you notice when you walk onto a beach or stand near the ocean at low tide. On Earth, that smell comes almost entirely from biological activity. Marine phytoplankton, microscopic ocean-dwelling organisms, produce dimethyl sulfide as a metabolic byproduct. It rises from the ocean's surface into the atmosphere, where it contributes to cloud formation and the characteristic smell of coastal air. When you breathe that scent in, what you are registering, it without knowing it, is the chemical exhaust of billions of living organisms processing the ocean around them. The reason this matters for K218b is that dimethyl sulfide, on Earth, does not appear in large quantities through any process that does not involve biology. And if K218b's atmosphere contains it, the implications are considerable. In April of 2024, the James Webb Telescope stared at K218b for approximately 6 hours using its MIRI instrument, a mid-infrared camera designed to analyze the chemical composition of planetary atmospheres by measuring which wavelengths of starlight the atmosphere absorbs as the planet passes in front of its star. 6 hours of observation time on the James Webb Space Telescope is not a casual allocation. The telescope's time is one of the most contested scientific resources on the planet, competed for by research teams from dozens of countries, and the committee that allocates it weighs proposals against each other with considerable scrutiny. The fact that 6 hours were committed to a single target tells you something about how seriously the scientific community was taking the question. The results of that observation were published in April of 2025, and they reported a dimethyl sulfide signal at 3 sigma confidence. 3 sigma means that there is approximately a 0.3% probability that the signal is the result of random noise rather than a genuine atmospheric feature. That sounds reassuring. 0.3% is a small number. But the standard that physicists use for a confirmed discovery is 5 sigma, which corresponds to a probability of roughly 0.00006%, a chance so small that you would need to run the same measurement approximately 3.5 million times before expecting a false positive by chance. 3 sigma is significant. It means something is probably there, but it is not confirmation. It is the difference between a strong suspicion and a verdict, and in the history of science, that gap has swallowed many results that initially looked promising. To reach 5 sigma, the researchers estimated they would need 16 to 24 more hours of James Webb observation time, a considerable additional commitment with no guarantee of what the outcome would be. And this is where the story becomes not just about K218b, but about something larger, something that touches the very nature of scientific discovery. Because we have been here before. Sarah Seeger, a planetary scientist at MIT and one of the foremost researchers working on atmospheric biosignatures, responded to the 2025 results with a caution that was direct and precisely measured. She noted that while the signal was worth investigating, the scientific community needed to resist the pull of the conclusion before the evidence had earned it. Her concern was not just about the statistics. It was about something the 3 sigma result could not address on its own, which was whether dimethyl sulfide on K218b even required a biological source in the first place. Because in 2024, the laboratory experiments demonstrated that dimethyl sulfide can form through abiotic chemical processes, non-living reactions that require no organisms whatsoever. And further complicating the picture, dimethyl sulfide has been detected in comets and in the interstellar medium, in molecular clouds between stars where no planet, ocean, or living thing has ever existed. The molecule that smells like the seaside, the molecule that on Earth is almost synonymous with biological activity, turns out to be something the universe can produce on its own through ordinary chemistry. Then, in the summer of 2025, NASA conducted an independent reanalysis of the James Webb data and found no conclusive evidence for dimethyl sulfide in K218b's atmosphere. Not a refutation, not proof that it was not there, but no conclusive evidence that it was. The 3 Sigma signal, the scent of the seaside on a world 124 light-years away, had softened into an open question with no clear resolution in sight. And the pattern should be recognizable by now, because we built the hope carefully. Red dwarf star, Hyson world, hydrogen atmosphere, ocean hypothesis, 6 hours of the most powerful telescope ever built, a molecule that living things produce, and then watched it become uncertain again. Not disproven, uncertain, which in some ways is harder to sit with than a clean refutation. We keep arriving at the edge of something, and then finding that the ground is not quite where we thought it was. And so you might find yourself thinking that the problem is simply a matter of time and technology, that if we build better instruments, wait longer, gather more data, the fog will eventually clear and we will know. That is a reasonable thing to believe. It is also, if you look honestly at the history of this search, almost certainly wrong. Not because science is failing, but because the problem we are trying to solve is not the kind of problem that better instruments alone can resolve. To see why, you have to go back, not to the 1990s, not to the last decade, but to the summer of 1976, when 2 landers named Viking 1 and Viking 2 set down on the Martian surface and did something no spacecraft had done before them. They scooped up Martian soil and ran chemistry experiments on it, right there, looking for signs of biological activity. One of those experiments was called the Labeled Release Experiment, and it was designed by a biochemist named Gilbert Levin. The principle behind it was elegant in its simplicity. You add a nutrient solution to the Martian soil, a solution containing carbon compounds that living organisms tend to consume, and you watch for gas to be released. If something in the soil is metabolizing the nutrients, it will breathe out, and when Viking ran that experiment on Martian soil, the soil breathed out. The instruments recorded a positive signal, a release of gas consistent with microbial metabolism, and Gilbert Levin spent the following decades arguing that what Viking detected in 1976 was, in fact, life. The scientific consensus moved in the other direction, and it concluded that the reactive Martian soil chemistry, driven by peroxides or other oxidizing compounds, could produce an identical signal without any organisms present. But here is the part that is easy to overlook. That explanation was never conclusively proven either. The Viking labeled release experiment produced a genuine result that has never been definitively explained as purely abiotic. It remains, almost 50 years later, genuinely ambiguous. And then, in 1996, the ambiguity arrived in a different form. This time, not from Mars directly, but from a rock that had traveled from Mars to Earth. The meteorite designated ALH 84001 was discovered in Antarctica in 1984, and scientists eventually determined that it had originated on Mars, had been blasted into space by an asteroid impact billions of years ago, and spent the intervening time traveling through the solar system before landing in the ice. When researchers at NASA's Johnson Space Center examined it closely in the mid-1990s, they found structures inside the rock, tiny, elongated forms that looked, under an electron microscope, like the fossilized remains of ancient bacteria. They found organic compounds. They found mineral deposits whose chemical signatures were associated with biological processes on Earth. The case seemed, to those researchers, compelling enough that on August 7, 1996, President Bill Clinton stood in front of the White House and addressed the nation, describing the findings as potentially one of the most significant discoveries in human history. The world held its breath for a moment, and then, over the following years, the case quietly came apart. The nanostructures turned out to be consistent with mineral formation processes that required no biology. The organic compounds were shown to be largely the result of contamination during the meteorite's time on Earth. The features that had looked so promising dissolved, one by one, into mundane geological explanations, not proven fraudulent, not shown to be impossible, just insufficient. Another edge that turned out not to be quite there. Then, in September of 2020, a team of astronomers announced that they had detected phosphine in the atmosphere of Venus, a molecule associated on Earth almost exclusively with biological or industrial processes, of floating in measurable quantities in the clouds of a planet with surface temperatures hot enough to melt lead. The announcement caused an immediate sensation. Venus had not been the focus of serious astrobiological attention, but suddenly it was, and the reason was that phosphine is not easily explained by any known abiotic chemistry in the Venusian atmosphere. The lead researcher Jane Greaves of Cardiff University and her collaborators published their results in Nature Astronomy, and then the scrutiny began. Other teams reanalyzed the spectral data and found that the original signal had been partially an artifact of data processing errors. The phosphine levels were revised downward significantly. Alternative atmospheric chemistry that might explain the signal without biology was proposed. Yet the excitement deflated over months rather than days, and the Venus phosphine detection settled into the same territory as its predecessors, not confirmed, not refuted, quietly uncertain. Viking in 1976, ALH 84001 in 1996, phosphine on Venus in 2020, dimethyl sulfide at K2-18b in 2023 through 2025. Each time, the arc is the same. A rigorous experiment or observation produces a signal that looks, by all available frameworks, consistent with biology. Each time, subsequent investigation finds ways to explain the signal without life, or, at minimum, finds the ambiguity deep enough that no conclusion can be drawn. And each time, the scientific community treats this as the process working correctly, which it is, and moves on to the next question. But a commentary published by the Rand Corporation in 2025 pointed to something in this pattern that the normal framing tends to obscure, which is that the repeated collapse of these results is not only a story about insufficient evidence, it is a story about something more fundamental, the standards of evidence themselves. What does a positive detection actually look like? What would it mean for data gathered by human instruments, interpreted by human minds, shaped by human frameworks for what constitutes chemistry consistent with life, to confirm the existence of something that has never been confirmed before? The honest answer is that we have no framework adequate for a discovery with no precedent. The pattern of excitement then doubt is not a bug in science, and it is science working correctly against a question it was never designed to answer. The philosopher Carol Cleland at the University of Colorado has written extensively about what she calls the problem of finding life as we do not know it. Her argument is precise and worth sitting with carefully. Every instrument we have built to detect life, every biosignature we have defined, every chemical signal we have decided to look for is derived from our understanding of life on Earth. When Viking looked for metabolic gas release, it was looking for the kind of metabolism Earth organisms perform. When researchers identified the nanostructures in ALH 84001 as potentially biological, they were comparing them to Earth bacteria. When astronomers flagged dimethyl sulfide as a potential biosignature, and they were reasoning from a molecule that living things on Earth produce, we have built the entire architecture of life detection from a sample size of 1. We are, in Cleland's framing, prisoners of our own biology. We are trying to recognize something we have never seen using only the features of the one example we already have, which means that a form of life organized around different chemistry, different molecules, different energy sources, could be radiating signals through every instrument we possess, and we might be constitutionally incapable of registering it as life at all. This is not a detection problem that a better telescope solves. It is a conceptual problem that a better telescope cannot even address. Some researchers have pushed this further with what is called the shadow biosphere hypothesis, the idea that life with a different biochemical basis might already exist on Earth right now, alongside the life we know, and we have not found it precisely because we only look for life that resembles the life we already understand. The surface of your skin, the soil in a garden, the water in a deep ocean trench, all of it has been surveyed for microorganisms, but surveyed using techniques designed to detect organisms that share our biochemistry. And we have not even left Earth yet, and already the limits of our framework are visible. Before we can recognize alien biology, we need to understand what makes biology itself tick. What are the rules? What are the exceptions? And most importantly, is which features of life on Earth are universal laws of nature and which are just accidents? Which brings us back to the question that has been threading through all of this. The question that started with a rock in Jezero crater and expanded outward through the atmospheres of distant worlds and through the long, embarrassing history of results that promised more than they could deliver. Are we alone? And the strange thing, the thing that should stop you before you even begin to answer, is that we assume we know what we are looking for. We assume that the search for life is essentially a detection problem, that somewhere out there, life either exists or it does not, and the task is simply to build instruments sensitive enough to find it. But what the last several decades of failed detections are quietly suggesting is that the problem runs much deeper than that, because before you can search for life, you have to know what life is, and it turns out that we do not know that as well as we thought we did. Here is the thing that makes this genuinely difficult to sit with. Every living organism on Earth, without exception, uses the same genetic alphabet, 4 letters: adenine, thymine, guanine, cytosine. Not 6 letters in some organisms and 4 in others, not a different set in organisms that evolved separately, but the same 4 letters in every bacterium, every plant, every animal, every fungus, every organism that has ever been found on this planet. And that genetic code is translated into proteins using the same set of 20 amino acids, at the same ones in a blade of grass as in a blue whale, as in the microbes living in volcanic vents 2 miles below the ocean surface. The energy currency that powers your cells, the molecule your body uses to store and transfer chemical energy, is the same molecule used by every other organism on Earth. Every biochemical reaction in your body happens in water. Every cell is filled with it. And this is not a coincidence of environment. It is a deep structural uniformity that runs through the entire living world, from the smallest bacterium to the largest tree, from the first organism that ever existed to whatever is living in the soil beneath your feet right now. The 4 pillars of it: carbon chemistry, water, the genetic code, cellular organization. Together they define life as we know it, and they define it so completely and so consistently that for a long time we assumed they defined life as it must be. But they do not define life as it must be. They define life as it happened to be once, about 4 billion years ago. Because what that uniformity is actually telling you is not that these are the only possible designs for living chemistry. What it is telling you is that every living thing on this planet traces its ancestry back to a single common origin. One ancestor, one population, one original version of life from which every branch of the tree grew. One tree of life, one data point. Sit with that for a moment. We genuinely do not know what is universal and what is accidental. And the reason we do not know is that sample size problem. One tree of life, one data point. Yet you cannot establish a universal law from a single example. You can observe what is. You cannot determine what must be. The genetic code could be 4 letters because 4 is the minimum required for sufficient complexity. Or it could be 4 letters because the ancestor that first used 4 letters happened to survive when others did not. The 20 amino acids could be the only amino acids capable of building functional proteins under Earth conditions. Or they could be 20 out of thousands of possibilities that simply became locked in before any alternative could compete. Carbon chemistry is extraordinarily versatile. There are more than 10 million known carbon compounds, a number that reflects the atom's unusual ability to form long, stable, complex chains. But whether carbon is the only element capable of forming the basis of living chemistry, or simply the element that happened to get there first on this planet, is a question we cannot answer from our current position, because we only have one example. This is where NASA's working definition of life becomes important, and it is worth understanding exactly why it was constructed the way it was. The definition reads, a self-sustaining chemical reaction capable of Darwinian evolution. That is it. There is no mention of carbon, no mention of water, no mention of DNA, or cells, or amino acids, or any of the specific machinery that defines life on Earth. The definition was deliberately written that way, as a kind of escape from the trap that the shadow biosphere argument had identified. Because if you define life by its substance, if you say life is carbon-based chemistry, organized in cells using a 4-letter genetic code, then you have simply redescribed Earth life, and you have built a search framework that can, by definition, only find what you already know exists. But if you define life by its process, by the capacity for self-sustaining chemistry and Darwinian evolution, then you have opened the door to forms of life built on completely different material foundations. And there is emerging evidence that self-sustaining chemistry is not a trick exclusive to the molecular machinery of Earth life. Researchers at the University of Wisconsin-Madison, led by Betul Kachar, have identified 270 autocatalytic reaction cycles, chemical systems in which the products of a reaction help catalyze the production of more of those same products, creating a kind of chemical self-reinforcement that shares at least the structural logic of a self-sustaining system, without requiring any of the specific molecules that Earth life uses. 270 distinct cycles, not all carbon-based, not all water-dependent. The field of assembly theory, which drew significant attention at a major gathering of researchers in 2024, is developing mathematical frameworks for identifying the signatures of cumulative, iterative chemical processes, the kind of processes that might leave detectable traces regardless of what the underlying chemistry actually is. The work is early. Yes, the questions are hard, but what it suggests is that the process NASA's definition points to, self-sustaining chemistry capable of evolution, may be far more chemically general than the specific version that happened to arise on this planet about 4 billion years ago. And we are going to need that kind of thinking, because when you look at what life has managed to do on our own planet, when you see where it has managed to survive and thrive, you realize that the limits of biology are far wider than anyone imagined even a few decades ago. And that thought, that life's underlying process may be far more chemically general than the specific version that arose on this planet, becomes far less abstract when you look at what that process has already accomplished here, in places where, by every reasonable assumption, it should have been impossible. In 1977, a deep-sea research submersible called Alvin was lowered into the Pacific Ocean near the Galapagos Rift, descending to a depth of roughly 2.5 kilometers. To give you a sense of what 2.5 kilometers of ocean looks like from the inside, the pressure at that depth is approximately 250 times the pressure of the air in the room you are sitting in right now. No sunlight penetrates below about 200 meters of ocean, which means that at 2.5 kilometers down, the darkness is absolute and permanent. Not the partial darkness of a cloudy night, not the temporary darkness of a room with the lights off, but a darkness that has never once been interrupted by anything resembling light since the ocean formed. The temperature of the surrounding water hovers just above freezing. The environment is, by any reasonable biological accounting, hostile to life in every direction simultaneously. Crushing pressure, total darkness, near freezing temperatures, and no access to the photosynthesis that drives essentially every food chain on the surface of the planet. What the Alvin crew found when they descended into that environment did not fit any model that existed at the time. There were vents in the ocean floor, cracks in the crust where seawater had seeped down into contact with hot rock and was being expelled back out at temperatures exceeding 300 degrees Celsius, far above the boiling point of water at the surface, sustained at liquid state only by the crushing pressure of the ocean above. Yet the water coming out of those vents was loaded with hydrogen sulfide and other chemicals that are toxic to most surface life. The vents themselves looked, in photographs, like chimneys, structures of precipitated minerals rising from the seafloor, billowing what looked like black smoke into the near-freezing water surrounding them. And clustered around those vents, in a zone of scalding, chemically saturated, lightless water at the bottom of the ocean, was an entire ecosystem. There were tube worms growing up to 2 meters in length, creatures as long as a tall adult person standing upright, anchored to the seafloor in dense colonies, swaying in the thermal currents coming off the vents. There were clams, crabs, shrimp, and microbial mats coating every available surface. And none of these organisms were wispy survivors clinging to impossible margins. They were thriving, in numbers and in size, in a way that suggested the vent environment was not a marginal habitat for them, but a richly productive one. The tube worms in particular require a moment of attention, because what makes them possible reveals something fundamental. They have no mouths. They have no digestive system in the conventional sense. What they have instead is an internal organ called a trophosome, which is packed with chemosynthetic bacteria, microorganisms that do not use sunlight to produce energy, but instead extract chemical energy from the reaction between hydrogen sulfide and oxygen. The bacteria live inside the worm, and the worm provides them with the raw materials they need. And in return, the bacteria produce the organic compounds the worm uses to grow. This is chemosynthesis, not photosynthesis. It is a completely different energy economy, one that requires no star, no surface, no atmosphere, and no access to anything that exists above 200 meters of ocean. The whole ecosystem runs on chemistry alone, on the energy stored in the chemical bonds of minerals being expelled from the interior of the Earth. They do not need the sun. They do not need the surface. They do not need anything except geology and water. And those two things, it turns out, are everywhere. But the hydrothermal vents, as radical as they were, still sat at the bottom of an ocean that was connected to the same biosphere as the surface. Yet what happened when researchers began looking not at the bottom of the ocean, but inside the rock itself, not 2.5 kilometers down through water, but 5 kilometers and more down through solid crust, pushed the implication further than even the vent discovery had. The deep biosphere is not a widely discussed subject outside of geomicrobiology, but the findings that have come out of it over the past few decades amount to a quiet demolition of the intuition that life exists on the surface of the Earth and tolerates brief excursions downward. What has been found instead is that microbial life exists in continuous, ancient communities at depths of 5 kilometers and beyond, inside rock formations that have been sealed off from the surface world for millions of years, communities that have not seen sunlight, have no connection to photosynthesis, and receive no material from the surface biosphere at all. The question of what these communities run on was answered, and the answer is genuinely strange. The rock surrounding these organisms contains uranium, thorium, and potassium, radioactive elements whose decay releases energy into the surrounding material, and that energy is sufficient to split water molecules into hydrogen and oxygen. The hydrogen becomes a fuel source. The microbes, in a very real sense, are eating radiation, not directly, but by consuming the chemical products that radiation generates when it encounters water in the dark interior of the Earth. They are powered by the slow, steady release of energy from atoms that have been decaying since before the Earth itself fully formed. Our researchers at the University of Colorado Boulder published work in 2025 on serpentinization, a related process in which water reacts with certain iron and magnesium-rich rocks to produce hydrogen and heat, confirming that the chemical energy available to deep biosphere communities is more widespread and more geologically durable than previous estimates had suggested. And the scale of this hidden biosphere is staggering in a way that forces a rethinking of what the word biosphere even means. Current estimates suggest that the total mass of microbial life living in the deep subsurface of the Earth may rival the total mass of all life living on the surface. Every forest, every ocean, every insect colony, every living thing you have ever seen or could imagine seeing are potentially matched in sheer biological mass by organisms living in darkness, in rock powered by radioactive decay, at depths that no human being has ever reached or ever will reach through direct excavation. Sit with that for a moment, because what it means is this: life, on this planet alone, has colonized an interior that is sealed from the surface, receives no energy from the sun, and operates on a completely different energetic logic from the one that powers every living thing visible to the naked eye. And if that is true here, then the obvious question is what happens when you take that logic and apply it to a world with no sun at all? Because there is a category of world that astronomers have known about for decades, but that rarely enters the conversation about life: rogue planets. Worlds that were ejected from their solar systems through gravitational interactions early in their histories, sent drifting through interstellar space billions of miles from the nearest star, in eternal and total darkness, with no prospect of receiving external energy of any kind. By the old model, those worlds were dead on arrival. By the logic of the deep biosphere, where radioactive decay generates heat, where that heat drives chemistry, where liquid water can persist in a warm interior even when the surface is frozen to temperatures near absolute zero, they are not obviously dead at all. They are worlds of eternal darkness, billions of miles from any star, that could, if the geology is right and the water is present, be alive in their interiors in a way that nothing on the surface would ever reveal. So the discovery of hydrothermal vent ecosystems was a revolution. It proved that life does not need the sun. It does not need photosynthesis. It does not need the surface. All it needs is liquid water, a source of chemical energy, and the right raw materials. And that changes everything about the search for life elsewhere, because the sun is just one star among hundreds of billions. But geology, water, and chemistry are everywhere. And when you look at our own solar system with that revised understanding, when you stop asking which worlds receive enough sunlight and start asking which worlds have liquid water and chemical energy, the list of candidates changes completely. And that revised understanding, that life needs only liquid water, a source of chemical energy, and the right raw materials, does not just apply to worlds with stars. It applies anywhere those three conditions are met, which is a far longer list than it used to be. But before we look outward at what that list includes, there is one more layer of this argument to work through. Because even granting everything the hydrothermal vents and the deep biosphere have taught us, most people still carry a set of assumptions about what environments life can and cannot physically tolerate. Radiation beyond a certain point kills everything. Temperatures above boiling are incompatible with biology. The vacuum of space is instant death. Pressure beyond a certain depth crushes cells into nothing. These feel less like assumptions and more like physics. And every single one of them has been crossed by something alive. Every time we draw a line and say life cannot survive beyond this point, some organism crosses it. The lesson is consistent, and it is humbling. Start with radiation. The standard measure used in medicine and radiation safety is the gray, the unit of absorbed radiation dose, and the amount that will kill a human being with near certainty, delivered all at once, is around 10 gray. Above that threshold, the damage to DNA accumulates faster than the body can repair it, and the result is death within days or weeks from radiation sickness. 10 gray is the wall. It is not arbitrary. It is the point at which the biochemical machinery that sustains life simply cannot keep up with the destruction being inflicted on it. And then there is Deinococcus radiodurans, and a bacterium small enough that millions of them could sit on the period at the end of this sentence, which was originally discovered living inside nuclear reactors, not near nuclear reactors, not in the vicinity of elevated radiation, but inside the cooling water of the reactors themselves, in an environment that would deliver a lethal dose to a human being in a matter of minutes. Subsequent research established that Deinococcus radiodurans can survive radiation doses not of 10 gray, not of 100 gray, but of thousands of gray, doses that exceed the threshold of human lethality by factors that make the word tolerance feel inadequate. The mechanism appears to be an extraordinarily efficient DNA repair system, one capable of reassembling a genome that has been shattered into hundreds of fragments, and stitching it back together correctly and resuming normal function. But the mechanism is almost beside the point. The point is that this organism exists in the real world, in conditions that our entire intuition about radiation and life said should be sterile. And it is not merely surviving there, but thriving. That wall is gone. Now consider temperature. Living cells require certain chemical reactions to proceed, and those reactions have ranges. Too cold and molecular motion slows below the threshold of function. Too hot, and the complex molecules that make cells work begin to denature, to unravel, to lose the precise shape that gives them their biological purpose. The canonical upper limit for life was long assumed to sit somewhere around the boiling point of water, and it is easy to see why. Our proteins cooked above 100 degrees Celsius do not, in ordinary experience, remain functional. Boiling is what destroys the biology in food. But thermophiles, microorganisms adapted to high-temperature environments, do not respect this ceiling, and the ones living in and around hydrothermal vents, in geothermal springs, in the superheated water of deep-sea vent systems, have been documented growing and reproducing at temperatures well above 100 degrees Celsius under the elevated pressures that prevent that water from turning to steam. The environment is actively boiling by the standards of what you experience at sea level, and there are living organisms running their metabolisms through it, sustaining themselves, reproducing. That wall is also gone. But perhaps no single organism has collapsed as many walls simultaneously as the tardigrade, a microscopic animal, typically less than 0.5 millimeter in length, sometimes described as looking like a slow-moving bear when viewed under a microscope, found in moss, in soil, in ocean sediment, in glaciers, in hot springs, essentially everywhere on Earth that anyone has thought to look. Tardigrades can survive near absolute zero, temperatures so cold that molecular motion approaches its theoretical minimum, the point at which chemistry as we understand it essentially stops. And they can also survive temperatures above 150 degrees Celsius, a thermal range wider than that of almost any other organism ever studied. They can survive pressures equivalent to roughly 6 times the pressure at the bottom of the Mariana Trench, the deepest point in any ocean, where the water above you would represent a column of pressure that would crush the structural integrity of most engineered objects. They can survive the vacuum of space, not a near vacuum, not low pressure, but the actual hard vacuum of open space, where there is essentially no atmosphere, no pressure, and direct exposure to ultraviolet radiation and cosmic rays, a condition that should be lethal to any cell with a membrane simply because of the pressure differential alone. Tardigrades survive it by entering a state called cryptobiosis, in which they shed nearly all of their water content, pull their legs inward, and reduce their metabolic activity to a level so close to zero that the distinction between alive and not alive becomes genuinely difficult to specify. They are not dead. They are also not, by any conventional biological measure, functioning. They are suspended somewhere in between, waiting, and when conditions return to something habitable, they resume. In 2019, an Israeli spacecraft called Bereshit crashed on the surface of the Moon. The crash was unplanned. The spacecraft was attempting a soft landing and experienced a technical failure during descent, impacting at high speed. Among the things it was carrying were thousands of tardigrades, included as part of an experiment payload, and the question of whether any of them survived the impact and currently sit on the lunar surface, dormant, in a state of cryptobiosis, is one that nobody has a definitive answer to. The Moon has no atmosphere. Its surface temperature swings from over 100 degrees Celsius in direct sunlight to below negative 150 degrees in shadow, and there may be tardigrades there, sitting in the dark, not dead, not alive in any active sense, simply waiting for conditions they will almost certainly never encounter again. So the revised picture is this: radiation in doses thousands of times lethal to humans, not a limit. Temperatures above boiling, not a limit. Pressures 6 times greater than the deepest trench on Earth, not a limit. The vacuum of open space, not a limit. The minimal requirements for life, it turns out, are shockingly minimal. And when you apply that understanding to our own solar system, and when you stop asking which worlds are Earth-like and start asking which worlds have liquid water and a source of chemical energy, you arrive at a list of candidates that would have seemed impossible to take seriously 50 years ago. And that is now the subject of active investigation with spacecraft either already in flight or already there. So when you take that revised understanding of what life actually requires, not sunlight, not stable surface temperatures, not gentle pressures, not any of the conditions we once considered non-negotiable, and you turn it outward toward the rest of the solar system, the first thing that happens is that a world you have probably written off as frozen and irrelevant stops looking irrelevant almost immediately. Europa is one of Jupiter's 4 largest moons, slightly smaller than our own moon, and if you could see it from close distance, what you would see is a surface covered in reddish-brown fractures running in long, arcing lines across a shell of ice, crossing and recrossing each other in a pattern that looks, with very little imagination required, like the surface of a cracked egg. That comparison is not decorative. Those cracks are evidence of motion, of a surface that has been pushed and pulled and stressed by forces operating from below, and the nature of those forces is the thing that changes everything about how you have to think about this moon. Beneath that ice shell, there is an ocean of liquid salt water, and it has almost certainly been liquid for billions of years. The depth of that ocean is estimated at somewhere between 50 and 150 kilometers. The honest answer is that we do not know the exact figure, and the range exists because measuring the interior of a moon from a spacecraft is extraordinarily difficult. But even the lower estimate, 50 kilometers, is already more than 4 times deeper than the deepest point in any ocean on Earth. When you take the full volume of water that number implies, accounting for the surface area of Europa and the likely extent of the ocean beneath its ice, you arrive at a total volume somewhere between 2 and 3 times greater than all the liquid water in all the oceans of Earth combined. Every ocean, every sea, every connected body of salt water on this planet, and Europa contains more than twice that amount, sitting in darkness under a shell of ice, about 630 million kilometers from where you are right now. And that is the scale we are discussing when we talk about Europa, not a frozen wasteland, the largest accessible reservoir of liquid water in the known solar system. The question, of course, is how an ocean that far from the sun stays liquid at all, because the surface of Europa reaches temperatures of around negative 160 degrees Celsius, and at that distance from the sun, solar energy alone would freeze any exposed water almost instantly. The answer is Jupiter. Europa orbits Jupiter in a gravitational relationship so intense that the tidal forces, the stretching and compressing that occurs as Europa moves through the varying gravitational field of the largest planet in our solar system, generate heat within the Moon's interior on a continuous basis. And the same basic process that generates heat in a bent metal coat hanger, except operating inside an entire moon, sustained indefinitely by orbital mechanics, and almost certainly producing hydrothermal activity on the ocean floor. This is not confirmed, but the Galileo spacecraft, which orbited Jupiter in the late 1990s, detected what is called an induced magnetic field around Europa, a field generated by the interaction of Jupiter's enormous magnetic influence with a layer of electrically conductive material inside the Moon. And salt water is electrically conductive. That was the first strong evidence that the ocean is not theoretical. Then, in January of 2026, researchers announced that salty ice at Europa's surface appears capable of sinking back down into the ocean, creating a slow cycle of exchange between the surface and the interior, which means the chemistry of that ocean and the chemistry of the surface are not permanently isolated from each other, and there is already a spacecraft on its way there to investigate. Europa Clipper launched on October 14, 2024, aboard a Falcon Heavy rocket, and it is the largest interplanetary spacecraft NASA has ever built. Its solar arrays span 30 meters from tip to tip, which is roughly the length of 3 full-sized school buses placed end to end. Because at Jupiter's distance from the Sun, the amount of solar energy available is small enough that you need an enormous collection area just to power the instruments. Those instruments number 9, and they include a radar system called Reason, specifically designed to penetrate ice and map what lies beneath it. In March of 2025, as the spacecraft was passing Mars for a gravity assist, the team activated Reason and ran a 40-minute test, collecting 60 gigabytes of radar data as the spacecraft descended from 5,000 kilometers to 884 kilometers above the Martian surface. Don Blankenship at the University of Texas at Austin, who leads the radar instrument team, described the test as successful in demonstrating the kind of ice-penetrating performance the mission will need. The spacecraft will receive another gravity assist from Earth in December of 2026, and it will arrive at Jupiter in April of 2030, after which it will conduct 49 close flybys of Europa, some passing within 25 kilometers of the surface, closer than many aircraft cruise to the ground. If the plumes that the Hubble Space Telescope has detected rising from Europa's surface are real and active during those passes, the spacecraft may fly directly through them, collecting what would amount to a taste of an alien sea gathered from orbit, without ever needing to land or drill. Are we alone? Europa. Clipper is, in a very literal sense, part of the machinery we have built to find out. But there is another world in this solar system that does not require us to wait for a spacecraft to arrive or to hope that surface plumes happen to be active on the right day, because it is already doing something that Europa only hints at. Enceladus, one of Saturn's moons, is roughly 500 kilometers across, smaller than the state of Arizona, and it erupts continuously. In 2005, the Cassini spacecraft discovered that Enceladus is venting enormous plumes of material from a series of fractures near its south pole called the Tiger Stripes, and Cassini did not just photograph those plumes from a distance, it flew through them multiple times. And what it found inside those plumes was, in terms of what it implies, almost difficult to process calmly. Water, organic compounds, salts, molecular hydrogen, which on Earth is produced by the interaction of hot water with rock on the ocean floor, the chemical signature of hydrothermal activity. And in 2023, researchers confirmed the presence of phosphorus in the plume material, completing what is called the CHNOPS set: carbon, a hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the 6 elements considered essential to all life as we know it. Enceladus is the only body beyond Earth where all 6 have been confirmed to exist together in liquid water. The concentration of phosphorus in the plume is estimated at more than 100 times its concentration in Earth's oceans. In 2025, James Holden at the University of Massachusetts Amherst ran laboratory experiments mimicking the conditions of a Europa-like ocean, using deep-sea vent microbes from Earth, and found that those microbes could survive and metabolize under those conditions. Enceladus has liquid water. It has hydrothermal activity. It has all 6 chemical building blocks. It has a source of chemical energy. And it is handing us samples of its ocean for free, continuously, yes, without any requirement that we drill or land or wait for a lucky alignment. We could, in principle, fly a spacecraft through that plume and directly sample the interior of an extraterrestrial ocean. And we have not even left our own solar system yet. But all of this, Mars, Europa, Enceladus, everything we have examined so far, rests on a particular assumption, which is that life anywhere would be built from roughly the same ingredients that life here is built from: carbon, water, familiar molecules assembled in familiar ways. That assumption may be correct, but what would alien life actually be made of if it were not? Not all life needs to run on the same chemistry as ours. That is where we go next, into the chemistry of the truly alien. That assumption, that life anywhere would need carbon, would need water, would run on the same molecular machinery that every organism on this planet has used for 4 billion years, is worth examining very carefully, because there is no physical law that requires it to be true. It is an observation, a sample. And as we have already established, a sample of one tells you almost nothing about the universe. Start with silicon. In the periodic table, silicon sits directly beneath carbon, which means it shares the same fundamental structure: 4 bonding sites, capable of forming long chains and complex molecular architectures in roughly the same way that carbon does. On paper, silicon looks like a plausible substitute. It can link to itself. It can link to other elements. And for decades, science fiction writers and scientists alike have asked whether a planet somewhere might host life built on silicon, the way Earth hosts life built on carbon. But when you examine the chemistry closely, the problem becomes visceral in a way that is hard to unsee. When carbon reacts with oxygen, you get carbon dioxide, a gas, exhaled, and released into the atmosphere, carried away. That is how carbon-based organisms dispose of a key metabolic byproduct. They breathe it out. When silicon reacts with oxygen, you get silicon dioxide. And silicon dioxide is not a gas. Silicon dioxide is quartz. It is glass. It is sand. A silicon-based organism running a metabolism that oxidizes silicon would have no way to exhale its waste. It would be producing solid mineral inside its own body, and the image that produces is not of a creature breathing. It is of a creature slowly filling with stone. Whatever silicon-based life might look like, it would face that chemical barrier at the most fundamental level of its metabolism, and no one has explained convincingly how it would cross it. But here is where it gets more complicated, and where the assumption that silicon is simply ruled out starts to crack. In 2016, Frances Arnold at the California Institute of Technology, who would later receive a Nobel Prize, engineered bacteria to create chemical bonds between silicon and carbon, bonds that do not form naturally under Earth conditions. She did not create silicon-based life, but she demonstrated that the boundary between carbon chemistry and silicon chemistry is not a wall. It is a threshold, and life, even Earth life with some directed pressure applied to it, can cross it. The 270 autocatalytic chemical cycles we have already encountered in the origins of life literature include non-carbon reactions. The building blocks of life are not as exclusively carbon's domain as we once assumed. Silicon may never form the backbone of a fully functional biochemistry the way carbon does, but the fact that biology can be pushed across that threshold at all changes how confidently we can say the word impossible. And if you move away from silicon entirely and instead ask what other solvents might replace water, the list of candidates is longer than most people expect. On Earth, water is the medium in which chemistry happens, the liquid in which molecules meet and react and assemble. But water is liquid only between 0 and 100 degrees Celsius at sea level. The universe contains temperatures and pressures that make those parameters look extremely narrow. Ammonia, for instance, is liquid between -78 and -33 degrees Celsius. That range sits well below anything we think of as habitable. And yet, the chemistry that ammonia supports is not empty. Ammonia can dissolve a wide range of compounds. It can form hydrogen bonds. It can serve as a medium in which complex organic reactions unfold. A world where ammonia is the solvent would be a world running at temperatures we would consider lethally cold. But the chemistry would not be inert. It would be a different canvas. The reactions would be slower. The energy flows different. But the fundamental requirement, molecules meeting in liquid, assembling, reacting, would still be met. And then there is Titan, which is not a thought experiment. It is a place, orbiting Saturn right now, with a surface temperature of -179 degrees Celsius and an atmospheric pressure about 1.5 times what you feel standing at sea level on Earth. Titan has lakes, not metaphorical lakes, literal standing bodies of liquid on a planetary surface, with shorelines and waves and evaporation cycles, photographed by the Cassini spacecraft. But the liquid in those lakes is not water, it is methane. Liquid methane, stable at Titan's surface, pooling in basins and flowing through channels the same way rivers flow on Earth under entirely different chemistry. The question researchers began asking is whether anything could live in it. It sounds like science fiction, but the physics is straightforward. In 2015, researchers at Cornell modeled a cell membrane, the fundamental boundary that separates the interior of a living cell from its environment, built not from the phospholipid bilayers that every cell on Earth uses, but from nitrogen-containing organic molecules that would be stable in liquid methane. They called it the azotosome. And what is genuinely strange about it is the geometry. On Earth, a cell membrane works the way it does because its molecules arrange themselves with water-repelling tails pointing inward and water-attracting heads pointing outward. The azotosome works by reversing that logic entirely, arranging its molecules to be stable in a liquid methane environment rather than a water environment. It is built inside out by Earth standards. The interior of such a cell would be the methane-compatible face, and the exterior would be the polar face, the opposite of everything evolution on this planet has ever produced. And the timescales such life might operate on would be extraordinary in their own right. Yes, because the chemical reactions that power biology slow dramatically at low temperatures. A single heartbeat might take hours. A single generation might last centuries. Life on Titan, if it exists, would not be something you could observe in real time with human patience. It would be life on a completely different clock. And if you find cold chemistry biology implausible, consider that the clouds of Venus, which we tend to think of as a dead and poisonous world, contain, at an altitude of roughly 50 to 60 kilometers, temperatures and pressures almost identical to what you experience standing outside on a mild day on Earth. The cloud layer at that altitude is not a vacuum and it is not a furnace. The solvent there is sulfuric acid, yes, which is corrosive by Earth standards and immediately hostile to everything we are built from. But sulfuric acid is still a liquid, still a medium in which chemical reactions can occur, and a small number of researchers have asked what chemistry might be stable within it, and whether the organic compounds detected in that layer might represent something more than contamination or inorganic processes. The answer is genuinely uncertain, but the point is that the same altitude that would destroy any Earth organism also maintains the kind of temperature and pressure that, somewhere else in the universe, we might call comfortable, and the only thing separating comfort from corrosion is what you are made of. We are not going to wait indefinitely to examine one of these alternative chemistry environments up close. Dragonfly. as a rotorcraft lander built by NASA is scheduled to launch in the late 2020s and arrive at Titan in the mid-2030s. It is, in a meaningful sense, a drone. It will fly through Titan's atmosphere, which, given the Moon's gravity at roughly 1/7 of Earth's and its atmospheric pressure at 1.5 times Earth's, provides almost ideal conditions for flight. And it will land at multiple sites, analyzing the chemistry of the surface, looking for the kinds of organic complexity that would suggest that liquid methane is not just a solvent sitting idle, but a medium in which something is happening. Dragonfly will not answer the question definitively, but it will bring us within instrument range of a world that challenges every assumption we carry about what life requires. And if it finds something, any signal, any chemical pattern that does not resolve into pure geology, then whatever we want to call it, it would represent the most consequential discovery in human history, not because of where it happened, but because of what it would mean about the rules. Because finding life on a different chemical basis would not just mean life elsewhere. It would mean life is not constrained to a single recipe. It would mean the universe is running more experiments than we imagined, in more solvents, at more temperatures, under more conditions than our one data point ever suggested was possible. But chemistry is not the only force that shapes what life can become. There is another force so fundamental and so inescapable that we barely think about it. That force is gravity. And the reason you do not notice it is that you have never lived without it. It pulled you into the world the day you were born, shaped the first breath your lungs took, and it will hold you down until the day you die. Every bone in your body, every muscle, every blood vessel, every joint and organ and inch of your anatomy exists in its current form, because evolution shaped it under one specific gravitational pull, the pull of one particular planet, of one particular size, orbiting one particular star. You carry that gravitational signature in your skeleton, the way a tree carries the record of its climate in its rings. And if you understand that, you begin to understand why the humanoid alien, the upright, bilaterally symmetrical, two-armed, walking creature of science fiction, is not a prediction. It is a projection. And it is what evolution looks like when you only have one example. The honest answer is that we cannot predict what alien evolution would produce. We can only follow the physics and see where it leads. And the physics is remarkably clear about one thing. Gravity is not a background condition. It is a sculptor. Change the gravitational pull of a world, and you do not just get the same animals in different proportions. You get different solutions to different problems, built from different constraints, shaped by a force that touches every architectural decision a body has ever made. Consider what happens on a world with roughly twice the gravitational pull of Earth. An animal trying to move across that surface is carrying twice the effective weight of its skeleton and organs with every step. And an evolution responds to that problem the same way an engineer responds to a structural load, by adding material where the stress is highest. The bones thicken, the joints widen and flatten to distribute the increased compression. The muscles deepen and shorten, because shorter muscle fibers under higher tension generate more force per unit of length, and length becomes a liability when the goal is not reach, but support. The result would be creatures that appear, from a human perspective, dense and low, pressed toward the ground as if the ground itself were pulling harder, which of course it is. Not slow, necessarily, but compact in a way that reflects the cost of being tall. Serpentine in their movement, perhaps, distributing the load across more contact points, their limbs shorter relative to their mass, as their torsos deeper and wider than anything you would find on Earth. They would look, if you could see them, like an architect's response to a brief that said, "Make it strong, make it survive, and do not let it fall." And flight on such a world becomes almost an impossibility, or at minimum, a radical compromise. The problem is mathematical in its structure. Wing area scales with the square of an animal's dimensions, double the size, roughly quadruple the wing. But weight scales with the cube, double the size, and you roughly multiply the mass by 8. On Earth, that relationship already constrains flyers to relatively modest sizes. The largest flying birds hover at the edge of what the atmosphere can sustain. On a world with twice the gravity, that ceiling drops dramatically. Any flying creature there would need to be small, dense, and moving at speeds that make lift more practical than it sounds. Not soaring, not gliding in graceful arcs, but something closer to bullets with wings, burning enormous amounts of energy to stay aloft for short bursts, trading the elegance of flight for the brute physics of velocity. Flight would exist, probably, because evolution finds its way into every available niche, but it would not look like anything you associate with birds or bats, or the feeling of watching something effortless rise above you. Now, reverse the conditions. A world with 1/4 of Earth's gravity presents evolution with a completely different brief. The square cube law relaxes. Structures that would collapse under their own weight on Earth become viable, even advantageous. The bones can afford to be thinner, and because they are bearing a fraction of the load. The muscles can be smaller, because the work of moving against gravity costs less. Trees on such a world could grow to heights that Earth's atmosphere and root systems would never permit, hundreds of meters tall, their trunks narrowing to a degree that would be structurally absurd here, reaching toward light without the constant negotiation between height and the weight of all that wood. And flying creatures could scale upward in size to a degree that would be genuinely difficult to believe. Whale-sized flyers are not impossible under low gravity. They are a reasonable consequence of what the physics permits. The ceiling that constrains Earth's flyers simply rises, and life, which fills every available space, would fill it, but the cost runs in both directions. A low-gravity organism, built for that environment, if you were to bring it to Earth's surface, would find itself in a world that its body was never designed to survive. Its thinner bones would face compression they were never shaped to carry. Its smaller muscles would be inadequate to the task of standing, of lifting its own chest against the resistance of gravity it had never known. It would not be ill. It would not be injured by any pathogen or predator. It would simply be crushed, slowly and completely, by the weight of being itself in the wrong place. In 1976, Carl Sagan and E. Salpeter published a paper that took this line of thinking somewhere it had almost never gone before, into the atmosphere of Jupiter. Jupiter has no solid surface to stand on, no ground in any meaningful sense, but it does have an atmosphere that is thousands of kilometers deep and layered in bands of different pressures, temperatures, and chemistries. Sagan and Salpeter asked, seriously and rigorously, what kinds of organisms the physics of that environment might permit. They described what they called sinkers, small organisms that drift downward through the upper atmosphere, feeding on organic chemistry, raining down from above, and die when the temperature and pressure below become lethal. They described hunters, faster organisms that pursue and consume others in the same layer, following the same basic predator logic you find in any ocean on Earth. And they described floaters, vast organisms, possibly kilometers across, that maintain their altitude through the same principle as a balloon, generating lighter than surrounding air gases internally to stay suspended in a layer where conditions suit them. Not swimming, not flying, floating, the way a jellyfish does in water, except that the medium is the atmosphere of a gas giant, and the organism is the size of a small city. Living weather systems, drifting through a sky that has no ground beneath it. Sagan did not claim these creatures exist. He was following the physics, and the physics did not rule them out. And that is the point. The same logic that produces a thick-set serpentine predator on a high-gravity rock produces a kilometer-wide atmospheric balloon on a world where the surface is a concept rather than a destination. Your skeleton is a record, every dimension of it, the thickness of your femur, the width of your pelvis, at the depth of your ribcage, was negotiated over hundreds of millions of years between the organisms that preceded you and the gravitational field of one planet. Change that field, and you change the negotiation, and you get a different record, pressed into different bones, or no bones at all. But gravity shapes bodies from the outside in. There is another layer of the question that goes deeper still, into how those bodies would perceive the world around them, what they would see, what they would hear, what reality would feel like from inside a sensory system built for a completely different environment. And before we get there is one more surface-level thing worth following, because even the color of life on other worlds would not look like what grows on Earth. 70% of the stars in the Milky Way are red dwarfs, cooler, are dimmer, redder than the sun, and a plant evolving under that kind of light would not reflect green back into the sky. It would need to absorb every photon it could, and the result would be forests that look, to human eyes, essentially black, soaking up the dim, red light with a thoroughness that leaves almost nothing to reflect. Under the blue-white light of a hotter star, the calculation shifts the other way, and vegetation there might appear silver or pale, deflecting the excess energy it cannot use. The jump in reflectivity at the boundary between visible and near-infrared light, what astronomers call the vegetation red edge, a signature produced by chlorophyll's specific absorption properties, would shift wavelengths on other worlds, and a telescope sensitive enough to detect it from light years away could, in principle, identify the color of a planet's photosynthesis. The Habitable Worlds Observatory, currently being designed, is intended in part to look for exactly that kind of signal, but color is only the surface. Beneath the surface, a deeper question lurks. Beneath the color of a planet's photosynthesis, beneath the shape of its creatures and the physics of their bones, there is a deeper question, whether evolution, given a second chance on a second world, would arrive at anything like the same solutions. And there is reason, real reason grounded in actual biology, to think it might. Consider what evolution has done on Earth when faced with the same problem in different places, with different raw material, across species that share no meaningful common ancestor. The eye has evolved independently somewhere between 40 and 50 times, and not refined, not inherited, independently, from scratch, with completely different optical architectures, in creatures that diverged from each other hundreds of millions of years before eyes appeared in either of their lineages. Flatworms evolved a simple pit of photoreceptors. Vertebrates evolved a lens and retina system. Mollusks evolved what is functionally a camera, complete with a curved lens and an adjustable aperture, and they arrived at it along a completely separate evolutionary road. The fact that so many different creatures, under so many different pressures, all converged on the same basic solution, something that detects light and converts it into spatial information, suggests that an eye is not a lucky accident. And it is what happens when biology runs up against the physics of electromagnetic radiation and tries to solve the problem of navigating a world that is full of it. Flight tells the same story 4 times over. Insects took to the air roughly 350 million years ago. Pterosaurs solved the aerodynamic problem independently around 230 million years ago, using elongated finger bones stretched into wings in a design that shares almost nothing structurally with what came before. Birds arrived with a solution built around feathers, evolving flight approximately 150 million years ago from a lineage that had never flown. And bats, 50 million years ago, solved it a 4th time, using elongated hand bones covered in membrane skin, a configuration different from all 3 previous solutions and yet subject to the same principles of lift, drag, and thrust, the same physics. 4 different answers, of 4 times arriving at the same destination by different roads. Simon Conway Morris, a paleontologist at Cambridge, has spent much of his career arguing that evolution is not random, wandering through biological possibility space. It is channeled, constrained, directed by the physics of the environment in ways that make certain solutions not just likely, but almost inevitable. Where there is light, something will probably evolve to see it. Where there is an atmosphere dense enough for flight, something will probably evolve to fly through it. Echolocation appeared independently in bats and in dolphins, 2 lineages that last shared a common ancestor deep in the mammalian tree, long before either of them had anything resembling sonar. Electric organs evolved in multiple completely unrelated groups of fish, in South America, in Africa. In marine environments, the same solution to the problem of sensing and communicating through murky water, arrived at again and again because the water is murky and electricity works. The universe, or at least this planet, seems to be pushing life toward the same answers from many different directions at once. And this is where the hope builds, because if you follow the logic of convergent evolution outward to other worlds, you arrive at a picture that feels almost comfortable. If an eye is something that physics makes probable wherever light exists and creatures need to find food, then perhaps the universe is full of eyes. If flight is something that aerodynamics keeps reinventing, then perhaps, wherever there are atmospheres, there are wings. Perhaps intelligence, the ability to model the world, to plan ahead, and to use learned information rather than only inherited reflexes. is itself a convergent solution, a thing that the pressure of complex environments keeps discovering independently, the way echolocation keeps being discovered wherever there are bats, or dolphins, or the equivalent. And there is real evidence for this too. Intelligence, broadly defined, has appeared in multiple lineages. Crows solve multi-step problems. Dolphins communicate in ways that suggest something like individual identity. Elephants mourn their dead and appear to recognize themselves in mirrors. Octopuses, which belong to a lineage that diverged from vertebrates something like 550 million years ago, before there were fish, before there were trees, can unscrew jar lids and navigate mazes and appear to distinguish between individual humans by face. Intelligence has evolved multiple times. That part is real. But technology has evolved exactly once. And the gap between those two sentences is where the hope quietly collapses. Because here is the thing about dolphins. They are, by any reasonable measure, highly intelligent. But they have no hands. A dolphin can learn, can plan, can communicate, but it cannot pick up a rock and shape it, cannot build a fire, cannot make a tool that persists after the dolphin is gone. The intelligence is there. The physical apparatus for translating that intelligence into cumulative material culture is not. Elephants live roughly as long as humans and are demonstrably capable of complex social reasoning, but their lifespan is constrained, and their generation time is long, in ways that slow the accumulation of transmissible knowledge. Crows are intelligent enough, but their bodies are small and their brain size is physically limited in ways that cap the complexity of what they can store and process. And octopuses, this is the part that deserves a moment of real attention. Octopuses die after reproducing. The females stop eating after they lay their eggs, and they devote their final weeks to tending those eggs, and then they die before the eggs hatch. Every octopus that has ever lived has started from scratch, with no accumulated knowledge from its parents, no inherited technique, no cultural transmission of any kind. Whatever an octopus learns in its brief life dies with it, completely, and the next octopus begins again at zero. There is intelligence in that lineage. There is no way for it to compound. So if you step back and look at the actual record of life on this planet, not the last few thousand years, not even the last few 100 million years, but the full 4 billion year record, something becomes clear that is not comfortable at all. For roughly 80% of the time that life has existed on Earth, the only life that existed was microbial. Not simple in the sense of being primitive or incomplete. Simple in the sense of being single-celled, prokaryotic, without nuclei, without multicellular bodies, without anything that you would recognize as an organ or a tissue or a limb. For more than 3 billion years, the entirety of life's achievement on this planet was microbes. Complex multicellular life appeared only around 600 million years ago. Mammals appeared around 200 million years ago. And the primate lineage that would eventually include humans appeared around 65 million years ago. The genus Homo has existed for roughly 2.5 million years. And technological civilization, the thing we mean when we imagine alien cultures sophisticated enough to build radio telescopes or generation ships, has existed for approximately 300 years, which is not even a rounding error in the history of life. If you compressed 4 billion years of biological history into a single 24-hour day, complex multicellular life would not appear until after 9 in the evening. Mammals would arrive around 11. Humans would appear in the final 2 minutes before midnight, and technological civilization would occupy the last fraction of the final second. That is the timeline. That is the actual record. And so the instinct to imagine that life elsewhere would follow the arc from microbe to complexity to intelligence to technology, that instinct is not based on the evidence. It is based on a sample of one, and that sample took 3 billion years to get through the part that produced nothing except microbes. The philosopher of biology Stephen Jay Gould proposed a thought experiment. If you could go back to the beginning of life on Earth and replay the tape, would you get the same result? He believed you would not. He believed that the specific path from single cell to primate was not a convergent solution being pushed toward inevitability by physics, but something more contingent, more fragile, more dependent on accidents and extinctions and timing that had no reason to go the way it went. The eye might be convergent, Technology might not be, and the 3 billion years of microbial dominance before complexity arrived is not a waiting period. It is not the prelude to the real story. It is the story. No plants, no animals, no fungi, no eyes, no brains, no wings, no teeth, just microbes, metabolizing, diversifying, filling every available chemical niche on the planet, building the oxygen atmosphere that everything else would eventually breathe, doing all of this with a competence and a thoroughness that is genuinely difficult to call anything other than success. Not a planet waiting for complex life to arrive, a planet where microbial life is the complete, fully realized, spectacularly successful answer to the question of what biology can do. That might sound disappointing. We want alien civilizations. We want someone to talk to. But before we explore what that disappointment means, there is another dimension to alien life that we have not considered. One that challenges not just what alien life looks like, but how it experiences reality. And that is worth staying with for a moment, because it shapes everything that follows. We have been talking about what alien life might be, about microbes and chemistry and the chemistry of oceans buried under ice. But we have been implicitly assuming something that we should examine much more carefully. We have been assuming that if alien intelligence existed, and if it communicated, we would have some plausible chance of recognizing what it was doing. That assumption deserves to be taken apart slowly. Close your eyes for a moment and think about how you experience the world. Light entering your eyes, sound vibrating your eardrums. The world arrives to you as a stream of photons in a narrow band of wavelengths. Your 3 types of photoreceptor cells happen to be sensitive to, combined with pressure waves in the air, moving at a frequency your eardrums happen to respond to. That is your window. That is the entire aperture through which you receive everything you have ever known. Every face, every landscape, every storm, every page of text. And the honest answer is that we cannot predict what alien evolution would produce. We can only follow the physics and see where it leads. And when we follow it, even here on Earth, what we find is that evolution has opened radically different windows in creatures that share this planet with us right now. The mantis shrimp, a small marine crustacean found in shallow tropical waters, possesses 16 types of photoreceptor cells. You have 3. Those 3 allow you to distinguish millions of color combinations through the mixing of red, green, and blue signals that your brain processes into what you call color. The mantis shrimp does not process its 16 channels by mixing them the way you mix yours. It operates more like a 16-channel spectral scanner, reading wavelengths ranging from deep ultraviolet to far infrared in discrete bands that human visual science is still struggling to fully characterize. What the world looks like through those eyes is not something you can approximate by imagining a richer version of what you see. It is a categorically different kind of seeing, a completely different relationship between the organism and the light that reaches it. We share an ocean with this animal, and it lives alongside us, and we have essentially no idea what it perceives. But vision is only one sense, and it is arguably the one we are most prone to treating as universal. Sharks do not navigate primarily by light or sound. They navigate by detecting the faint electrical fields generated by the muscle contractions and nerve impulses of other living things. Every time your heart beats, it generates a small electrical pulse that propagates through the water around you. A shark can feel that pulse. It can track the animal generating it even when that animal is completely invisible, even when it is buried in sand, even in water so murky that light carries no useful information at all. Electroreception is not a supplement to the shark's other senses. For many species, it is the primary map of the world, and the mechanism by which the environment resolves from blur into legible detail. Birds and sea turtles add another layer entirely, perceiving the planet's magnetic field in a way that gives them a continuous orientation signal we still do not fully understand. An internal compass that is not a metaphor, but a genuine sensory channel that integrates geomagnetic information into the animal's moment-to-moment experience of space. And pit vipers see in infrared, detecting the heat signatures of warm-bodied prey in complete darkness through a pair of sensory organs that build a thermal image of the environment as sharp and actionable as anything your eyes deliver in daylight. These senses exist on Earth in animals we can observe and study. They evolved here, under this sun, in this atmosphere, competing in the same ecological theatre we occupy. And they are already so foreign to our own experience that the research literature on electroreception, magnetoreception, and infrared sensing is full of careful hedging about what these animals actually perceive, because we have no first-person access to the experience, and our instruments can only measure the inputs, not what the nervous system does with them. That is the gap, and we have not even addressed the deepest question yet. What happens when you take these principles off Earth entirely, on a world without sunlight, a moon orbiting far from its star, or a rogue planet drifting through interstellar space with a liquid water ocean kept warm by geological heat? There is no selection pressure favoring eyes sensitive to visible light, but sonar would be extraordinarily useful, and not the rough ambient sound navigation that bats use, but something refined over hundreds of millions of years of evolutionary pressure into a sensory system of extraordinary precision. Sonar sophisticated enough to resolve the internal structure of objects, to hear through solid material the way medical ultrasound images through your body's tissues. A creature that evolved over geological timescales in that environment would not merely detect the surface of the world, it would perceive the interior of it. Its experience of a rock would include what was inside the rock. And we have not even addressed the deepest question yet of how that changes what communication looks like for a civilization that evolved from such a creature. Because communication systems grow from sensory systems. As the internet you use is built on light and electricity because your civilization evolved from creatures that navigated by light, processed information electrically, and manipulated the physical world with appendages sensitive to pressure and texture. A civilization that evolved from chemosensory organisms, creatures for whom the primary information channel was molecular, the way scent works, but orders of magnitude more precise, would build its communication technology around molecular release and molecular detection. Its language would be chemical. Its libraries would be repositories of complex molecular sequences. Its equivalent of a radio broadcast would be an information-dense plume of molecules drifting through a medium. We would not recognize that as communication. We would analyze it as chemistry, but we would call it interesting and move on. A sonar-based civilization's equivalent of the internet might be acoustic, not sound waves in air, but pressure waves through whatever medium the civilization inhabited, carrying structured information in patterns of compression and frequency that would require us to first recognize them as structured, then recognize the structure as intentional, then recognize the intention as communicative, and then attempt to decode a symbol system built on a physical modality our nervous systems have no direct access to. And we have not even addressed the deepest question yet of whether we would even be looking in the right direction when those signals arrived. Consider what we already cannot do on Earth. Researchers studying humpback whale communication have been working since at least 2023 and 2024 to decode the structure of whale song. Animals that share our biology, that breathe air, that evolved from the same mammalian ancestor we did, that we can observe directly, record with hydrophones, and study in controlled interaction experiments. We still cannot decode what they are saying to each other in any meaningful semantic sense. We can describe the acoustic structure. We can identify patterns that recur. We cannot tell you what those patterns mean to the whale. And that is an animal that shares roughly 80% of its genome with you, that has lived in the same ocean you swim in, that we have been studying intensively for decades. Yet though the distance between us and a humpback whale is vanishingly small compared to the distance between us and a hypothetical organism that evolved independently on another world entirely, if the whale's communication system is already beyond our decoding, and it is, then alien communication built on chemistry, or sonar, or magnetic field modulation, or something that does not have a name in any human language, would be present in the universe in the same way dark matter is present, exerting effects, following physical laws, real and structured, and there, but undetectable by any instrument we have thought to build. Because we have thought to build instruments for the senses we have been searching for radio signals for more than 60 years, and the assumption behind that search is that any technological civilization would pass through a radio phase, would broadcast electromagnetic signals in the frequency ranges we scan, and that those signals would be detectable across interstellar distances. That assumption is not absurd. Radio is a real technology with real physics behind it, and it is plausible that civilizations would discover it. But radio may be a brief phase. Human civilization has been broadcasting detectable radio signals for roughly a century, and already we are migrating our communication toward lower power transmission, fiber optics, and directional signaling that leaks far less into space than the mid-20th century broadcasts that first made us theoretically visible. And listening for radio from an alien civilization might be like listening on a channel that nobody uses anymore, scanning for telegrams after the world moved to optical fiber, waiting for a signal type that was real and important for a narrow window, and then gave way to something else entirely. And the octopus complicates this even further, not as a communicator, but as a model for what intelligence can look like from the inside. The octopus has roughly 500 million neurons, roughly the same order as a dog, but the majority of those neurons are not in its brain. They are distributed throughout its 8 arms, which contain neural clusters capable of making local sensory and motor decisions without consulting the central brain at all. If you watch an octopus navigate a complex environment, yet you are watching a mind that is not located in any one place. The processing is distributed across the body in a way that makes the question of where the thought happens genuinely difficult to answer. The mind is here. You cannot point to any single location and say, that is where the octopus lives. Now imagine a colonial organism, or a networked chemical intelligence, or a distributed electromagnetic field processing system that evolved over billions of years on a world with different physics. And then ask yourself what its signature would look like from 30 light years away. Ask yourself whether any instrument we have built would distinguish it from background noise. In the summer of 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos, and in the middle of an ordinary conversation, and he asked a question that has haunted science ever since. Where is everybody? The logic behind the question is simple and devastating. The Milky Way contains somewhere between 200 billion and 400 billion stars. The universe is 13.8 billion years old, and our own sun, at 4.5 billion years old, is younger than a substantial fraction of the stars in the galaxy, meaning that if technological civilizations arise anywhere near as readily as life itself seems to, many of them would have had billions of years longer than we have had to develop, to spread, to leave some kind of mark. And yet, the sky is silent. No signals, no probes, no megastructures, no evidence of anyone at all. The silence is not a technical problem with our instruments. It is a fact about the universe that requires an explanation. If something is blocking the emergence of detectable civilizations, or ending them, or making them invisible to everything we have thought to look for, what that something is, that question does not have an answer yet. But the shape of the answer, when it comes, will tell us something about the future that no other question can reach. Something is blocking the emergence of detectable civilizations, or ending them, or making them invisible to everything we have thought to look for, and that something needs a name. The question that Fermi asked in 1950 did not come with an answer attached, but in 1961, a radio astronomer named Frank Drake proposed a way of at least thinking about the problem systematically. He wrote down a sequence of terms: the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually arises, the fraction where intelligence emerges, the fraction that develops detectable technology, and the length of time those civilizations remain detectable. And multiply them together, and you get an estimate for how many communicating civilizations might exist in the galaxy right now. It looks like an equation. It has the structure of an equation. But calling it an equation implies that we know what values go into it. And that is where the framework quietly falls apart. Because the first few terms, star formation rates, the frequency of planetary systems, we can actually measure those now with reasonable confidence. The later terms, the fraction of planets where life begins, the fraction where intelligence arises, the fraction that survives long enough to be detected, those are not measurements. They are placeholders for our ignorance, variables that could each span 12 orders of magnitude without anyone being able to say with certainty which end of the range is closer to the truth. Yet Drake did not solve the Fermi paradox. He built a precise machine for displaying exactly how deeply we do not understand it. And are we alone? That question, which once felt like an open invitation to the imagination, starts to feel different once you understand that the silence in the Drake equation's later terms is not a gap we expect to fill next decade. It might be a gap that reflects something real and terrible about the universe. In 1998, an economist named Robin Hanson published a paper that gave the silence its sharpest possible interpretation. He called it the Great Filter. The argument is straightforward and takes about 30 seconds to understand and then stays with you for the rest of your life. If the universe is this old and this large, and stars have had billions of years longer than ours to produce technological civilizations, and yet the sky is completely silent, then somewhere on the path from dead chemistry to a civilization that can make itself heard across the galaxy, something stops. Almost everything that tries to pass through it. Some step, one step, possibly, or a combination of steps, is so improbable, so unlikely, so brutally demanding that virtually nothing makes it across. That is the filter. And the question that keeps scientists awake is not whether the filter exists. The evidence strongly suggests it does. The question is where it sits on the timeline. Is it behind us or ahead of us? If it is behind us, if the hard step was something that already happened, is something we have already passed through, then the most likely candidate is the origin of life itself. Maybe the chemistry that builds a self-replicating molecule from raw ingredients is so extraordinarily unlikely that it happens perhaps once per galaxy per billion years, and we are among the vanishingly rare exceptions. If that is true, then the silence makes sense, and we are not doomed, just lucky. That is good news. The filter behind us means the road ahead is open. But if the filter is ahead of us, if life begins readily, if intelligence emerges with some regularity, if civilizations manage to develop radio telescopes and fusion reactors and all the apparatus of technological society, and then something ends them, then every silent sky is a graveyard. Every star without a signal is a civilization that got this far and did not get further. That is very bad news. And here is where the argument takes a turn that is genuinely difficult to sit with. Paradoxically, finding alien life would be terrifying because it would mean the Great Filter is probably still in our future. Let that sink in. The thing we are hoping to find is the thing that should frighten us most. If we send a probe to Europa and it returns samples teeming with microbial life, that discovery, which would feel like the greatest moment in the history of science, would simultaneously be evidence that the filter is not the origin of life. Life begins, apparently, in the cold, dark oceans of ice moons. It gets started, and if it gets started readily, then the silence above us is not explained by the rarity of life. It is explained by something that happens later, something that civilizations encounter after they have already crossed all the early hurdles, something that we have not encountered yet. The more places we find life, the more the filter moves forward in time, and the closer it gets to where we are standing right now. In October of 2025, the Austrian Academy of Sciences published a study that tried to put numbers on the scale of the problem, and the numbers are worth sitting with carefully. The study estimated that the nearest technological civilization to us is likely somewhere around 33,000 light-years away. To appreciate what that means, consider that light, which crosses the room you are sitting in so fast the delay is unmeasurable, takes about 8 minutes to travel from the Sun to the Earth. At 33,000 light-years means that even a signal traveling at the speed of light, the absolute physical speed limit of the universe, would take 33,000 years to reach the nearest civilization. Their reply would take another 33,000 years to return. A single exchange of 2 messages would span 66,000 years. The entirety of recorded human history, from the earliest clay tablets to the first text message, covers roughly 10,000 years. A single conversation with our nearest neighbors would take 6.5 times longer than all of that, not back and forth. 1 message, 1 reply. The study also found that for 10 technological civilizations to coexist in the galaxy at the same time, just 10, out of 400 billion stars, each one would need to survive and remain detectable for at least 10 million years. 10 million years. Anatomically modern humans have existed for roughly 300,000 years. Our civilization in the sense of settled agriculture and organized society, is about 10,000 years old. Our industrial civilization, the one that reshapes planetary geology and produces signals detectable from space, is perhaps 300 years old. And our nuclear weapons capability, the point at which we became physically capable of ending ourselves within an afternoon, is roughly 80 years old. The breakthrough. Listen Initiative has been scanning the sky with the most sensitive instruments ever built for this purpose, and the result is the same unbroken quiet it has always been. 10 million years is the minimum. 300 years is what we have managed. That is a sobering number. So, what would first contact actually look like? Not in the movies, not in our imaginations, in reality. And alongside that question sits another one worth turning over. Maybe the silence is not because civilizations destroy themselves. Maybe there are other explanations. The zoo hypothesis. Civilizations that transcend physical communication. Intelligence so different from ours that it does not occur to them to broadcast. Or the eschaton hypothesis that something more specific and structural governs what civilizations become. Each of those possibilities sounds plausible, and none of them is testable, at least not yet. So what would first contact actually look like? In reality, stripped of everything the movies have layered onto the idea over the past century? Not the blinding light over a city, not the transmission decoded by a brilliant loner working through the night, not the slow descent of a craft larger than a mountain, settling into a field while the world watches. The honest answer, the one that the history of science actually supports, is that first contact will almost certainly be a scientist frowning at an anomaly. It will be a data point that does not fit the expected pattern, flagged in a spreadsheet, sent to a colleague, questioned, rerun, questioned again. It will be a result that cannot be published for 3 years, because the peer review process, which exists precisely because anomalies are usually noise, demands that every alternative explanation be exhausted first. First contact will not arrive with a bang, it will arrive with a data point, and the world will not know to celebrate it for years. We are already living through the early stages of first contact. We just do not recognize it yet, because it does not look like the movies told us it would. Consider what we have been discussing this entire time. A rover on Mars spent 3 years driving across a dry lakebed to reach a rock formation, drilled into a surface the size of a piece of paper, and found concentric reaction fronts, leopard-spotted discolorations, and an organic carbon signal stronger than anything previously detected on another planet. The scientists who found it did not hold a press conference announcing the discovery of life. They published in Nature. It assigned it a 7 on a scale designed specifically to resist premature conclusions, and continued arguing about what it means. That is not a failure of courage. That is exactly what the first detection of extraterrestrial life would look like in its earliest hours. The Cheyava Falls leopard spots are not a confirmed answer. They are the kind of thing that, in 20 years, might be recognized as the moment when the answer first appeared, hiding in plain sight inside a small, arrowhead-shaped rock in Jezero crater. And 124 light-years away, a telescope that took 30 years to design and build is staring at a planet 8.5 times the mass of Earth, trying to determine whether a faint chemical signal in an alien atmosphere is produced by living organisms or by some process we do not yet understand. The researchers working on K2-18b need somewhere between 16 and 24 more hours of observation time to bring that dimethyl sulfide signal from 3 sigma to 5 sigma, which is to say, from statistically suggestive to scientifically confirmable. They are waiting for telescope time in a queue shared with every other question humanity is currently asking of the universe. This is also what first contact looks like. It looks like waiting for telescope time. But there is a development happening in parallel with all of these missions that deserves careful attention, because it addresses something that has quietly constrained this entire search from the beginning. The problem is epistemological. It is not that we lack instruments powerful enough to detect biosignatures. It is that the patterns biology leaves behind are often subtle enough that human pattern recognition, even expert human pattern recognition, struggles to separate them reliably from the background noise of geology and chemistry. In 2023, a study published in the Proceedings of the National Academy of Sciences It tested whether artificial intelligence trained on mass spectrometry data could distinguish biological samples from non-biological ones. The accuracy was approximately 90%, even when the samples were ancient, even when the biological material had been degraded for millions of years, even when what remained was not life itself, but something more like the chemical ghost of a pattern that living systems had once imposed on their environment. 90% accuracy detecting chemical ghosts in ancient mudstone. Yet that number is worth sitting with for a moment, because it suggests that the signature of life is more durable and more detectable to the right kind of analysis than most people assume. What the AI is reading is not a cell, not a fossil, not a structure. It is a statistical tendency. Living systems do chemistry differently than non-living systems do, and they do it in ways that accumulate into patterns visible at the molecular level long after the organism itself has ceased to exist. One of the clearest of these patterns involves isotopic ratios. Carbon comes in two stable forms, carbon-12 and carbon-13. Life, when it builds its molecules, preferentially incorporates carbon-12 because enzymes are slightly better at handling the lighter isotope. This preference is subtle, a fraction of a percent, but it is consistent, and it persists in the rock record for billions of years. When you find ancient carbon with the wrong ratio, too much 12 relative to 13, you are not looking at life. You are looking at the record of a decision that life made, repeated trillions of times, fossilized into the chemistry of stone. That is not a metaphor. That is a measurement. Another pattern is chemical disequilibrium. Oxygen and methane cannot coexist in an atmosphere for long without reacting with each other, which means that any planet sustaining both simultaneously must be continuously replenishing at least one of them. The only known mechanism for replenishing both at geologically significant rates is biology. If a future telescope detects oxygen and methane coexisting in the same atmosphere, that coexistence is itself a biosignature, and not because either gas is inherently biological, but because their presence together implies a process that prevents equilibrium from being reached, and life is the most compelling candidate for that process. NASA is currently building standardized databases that would allow future rovers to carry versions of this analytical capability in real time, not sending data back to Earth for processing that takes days or weeks, but running pattern recognition on site, flagging anomalies as they are encountered, directing sampling decisions toward the results most likely to yield answers. The Mars Sample Return mission has not yet launched, and K2-18b still needs more observation time, and the tools that might finally give us a definitive answer are still being assembled and tested and refined. But they are being assembled, and the databases are being built. The algorithms are being trained on every sample of Earth life and ancient Earth rock that researchers can feed into them. The infrastructure of detection is being constructed right now, instrument by instrument, dataset by dataset. But the type of life we find, or do not find, determines the consequences. And those consequences escalate in ways that most people have never considered. And those consequences are not equal. They do not sit on the same shelf, waiting to be examined with the same degree of calm. Each possible answer opens a door, and behind each door is a room larger than the one before it. And the size of the room determines how much of everything we thought we understood has to be rebuilt from the ground up. Start with the smallest answer. Microbes. Ancient, simple, here microbial life somewhere beyond Earth, in the sediment of Cheyava Falls, or dissolved into the subsurface ocean of Europa, or stirring in some cold chemical equilibrium beneath the ice of Enceladus. That would be a profound discovery, the most consequential in the history of science. The kind of finding that gets its own category in the permanent record of what humanity has learned, but sit with what it would actually mean at the level of implication, not just the level of announcement. If life arose independently on Mars, or on Europa, or anywhere else within the same solar system where it arose on Earth, then the chemistry of life is not a miracle. It is not an extraordinary accident, requiring an impossible sequence of contingencies. It is what chemistry does under the right conditions when given enough time. And it is a tendency of matter, and if life arises wherever the conditions allow, then in a galaxy containing several 100 billion stars, most of them older than our Sun, many of them orbited by rocky planets with liquid water and organic chemistry, The number of living worlds is not small. The galaxy is not empty. It is full. Microbial life, boring as that word sounds when you say it out loud, would mean that the cosmos is saturated with biology in the same way that Earth's oceans are saturated with it, at every depth, in every temperature range, in every chemical niche that can sustain a reaction. That is not a modest revision to our understanding. That is a restructuring of the entire frame. But there is a complication, and it sharpens rather than softens the weight of the discovery. Because if life is common, if microbial biology is what matter does when conditions allow, then the universe has had billions of years to produce it in billions of places. And some of those places would have progressed. Some of that chemistry would have crossed the threshold from microbial to complex, from complex to intelligent, from intelligent to technological. The question of why we have not heard from any of them, which Enrico Fermi first posed as an offhand remark over lunch in 1950, does not go away if we find microbes. It intensifies. Finding microbial life would push what scientists call the great filter, the barrier that prevents life from expanding into the observable universe, further forward in time, closer to us, closer to now. It would mean the filter is probably not behind us, and it would mean it lies somewhere between what we already are and what we might one day become. That is the version of the microbe discovery that does not make the headlines. The discovery itself is beautiful. The implication underneath it is vertiginous. The second answer is complex life, animals, plants, something with eyes or roots or nervous tissue, something that moves through an environment and responds to it with more than chemistry alone. If we find that, if some future telescope detects a biosignature consistent with complex multicellular biology on a world orbiting another star, then what the last 400 years of science have been slowly demonstrating becomes impossible to ignore. The Copernican revolution began in the 16th century with the demotion of Earth from the center of the solar system, and it continued with the recognition that the Sun is an ordinary star, that the Milky Way is an ordinary galaxy, that the observable universe contains more galaxies than the human mind can hold as a number. Each step has said the same thing in a louder voice. You are not special in the ways you thought you were. Complex life elsewhere would say it once more, and this time about biology itself. Evolution would not be our invention. Natural selection, the blind accumulation of inherited advantages, the patient sculpting of form by environment over millions of years. That process would be written into the laws of nature, the way gravity is written in, the way electromagnetism is written in. The universe would be not merely alive, but creatively, diversely, wildly alive, generating complexity wherever it has the raw materials and the time. Every lesson from convergent evolution on this planet, the eye arising independently dozens of times, flight solved separately by insects and pterosaurs and birds and bats, echolocation arrived at by both bats and dolphins without any shared inheritance, would be a local preview of what the cosmos does at scale. Evolution would be a cosmic law. And then the third answer, intelligence, a signal, a structure, a pattern in the data that cannot be explained by physics or chemistry, that requires a mind to produce. If that day comes, then the thing we have spent recorded history treating as our most private possession, consciousness, the inner experience of being alive, is not a local accident, and it is not the improbable byproduct of one particular lineage on one particular planet that happened to survive long enough to generate nervous tissue of sufficient complexity. It would be a property of the cosmos itself, something the universe tends toward, something that emerges wherever the conditions allow and the time is sufficient. The philosopher in you wants to resist that claim, wants to insist that our consciousness is ours, singular, unrepeatable. The evidence, if it arrived, would make that resistance hard to maintain, not because we would stop being what we are, but because what we are would turn out to be what the universe makes, over and over, in the dark. But suppose the signal came from 33,000 light years away. Suppose it arrived tonight, clean and unmistakable, a pattern in the radio spectrum that could not be noise. The message would have left its origin before the last ice age ended on Earth, before the first human civilization planted its first crop, before any of the history you have ever read had happened. A reply, sent at the speed of light, would travel for another 33,000 years before arriving. The round trip, One exchange of information, one question and one answer would take 66,000 years. Every civilization that has ever kept a written record, every dynasty and republic and empire and language, the entire span of human history as a documented phenomenon, fits inside half of that round trip with room remaining. Yet there is no conversation at that distance. There is only the knowledge that something existed, that it was capable of reaching across the void, and that by the time you learned of it, everything about it may already be gone. But there is another possibility, and it arrives with a quietness that the others do not have. What if we search and search and search, with every instrument we can build, every algorithm we can train, every mission we can launch, and we find nothing? What if Mars was always dead? What if Europa's ocean, when we finally sample it, contains nothing but chemistry? What if every exoplanet atmosphere we analyze returns data that is perfectly, completely, devastatingly explained by geology and physics alone? What if the silence is real? Then every thought you have ever had is unique in the cosmos. Not metaphorically unique, literally, physically, irreplaceably unique. Every conversation that has ever taken place between two human beings, every piece of music composed and played and heard, every act of care between one person and another, every moment in which a mind encountered something beautiful and recognized it as beautiful, all of it would be the only example of its kind in a universe 13.8 billion years old. There is no backup. There is no other instance running somewhere in parallel. The entire project of consciousness and meaning and art and science and love would be a single flame in a darkness that extends, as far as we can determine, without interruption to the farthest edge of what exists. A vast, beautiful, intricate machine running in an empty room. And the weight of that image cuts in both directions simultaneously. It is the most isolating thought the human mind can hold, and it is also the most clarifying, because it means that everything we do here, everything we protect and build and pass forward, is not one story among many. It is the only story being told, but we do not know yet, and that uncertainty is itself a gift, because the tools to answer the question are not hypothetical. They are being built and launched right now. So here is where we have arrived, and it is worth sitting with how far that is from where we started. We began with a rock the size of a small door, arrowhead-shaped, pulled from the floor of an ancient Martian lake by a rover that had driven for 3 years to reach it. On that rock, these scientists found leopard spots and concentric rings and an organic carbon signal stronger than anything Mars had returned before. And the minerals surrounding those signals were the kind that, on Earth, you find where life has been. From that rock, the argument opened outward the way a map does when you unfold it, past the hydrothermal vents at the bottom of the Pacific, where tube worms grow 2 meters tall without ever knowing the sun exists, past the geysers of Enceladus, carrying phosphorus and molecular hydrogen out through cracks in a moon of Saturn, past Europa's ocean, locked beneath kilometers of ice and heated from below by the gravitational pull of the largest planet in the solar system. It passed the methane lakes of Titan, where chemistry that life might one day exploit sits frozen and patient at 179 degrees below zero, past the clouds of Venus, where temperatures and pressures briefly resemble a mild afternoon on Earth, past the question of whether silicon could do what carbon does, past the signals drifting in the atmosphere of a world 124 light-years away, where something, geology or biology, and we do not yet know which, appears to be producing dimethyl sulfide, past the accumulated silence of half a century of searching, and the accumulated weight of an equation written in 1961 that has never been fully solved. All of it leads here, to this moment, to the question of what we do with everything we now know. And what we do is keep going. And that is not a small thing to say. The missions in flight and in planning right now represent a commitment that no previous generation of human beings could have made, because no previous generation had the instruments to make it meaningful. Europa Clipper is already moving through the outer solar system, carrying 9 instruments and a schedule of 49 close flybys, some of them passing within 25 kilometers of Europa's surface, close enough to taste whatever the ice is exhaling. The James Webb Space Telescope is spending its precious observing hours on the TRAPPIST-1 system, 40 light-years away, 7 rocky planets orbiting a red dwarf star, 3 of them sitting in the zone where liquid water could persist on a surface. Yet the most concentrated collection of potentially habitable worlds we have ever found at that proximity. The Rosalind Franklin rover, expected to launch in 2028, will drill deeper into Martian soil than any instrument before it, reaching layers that the surface radiation has never touched, where if anything biological persisted, it would have had the best possible chance of preservation. The European Space Agency is in the planning stages of a dedicated Enceladus mission, because the data Cassini returned before it was deliberately crashed into Saturn made it impossible to justify not going back. Dragonfly will reach Titan in the mid-2030s and fly through its thick amber atmosphere like a rotorcraft on a world where the chemistry of early Earth may be playing out in slow motion, frozen and preserved. The Habitable Worlds Observatory is still in its design phase, but when it reaches space, it will be capable of directly imaging Earth-like planets around nearby stars and reading the light that passes through their atmospheres for the signatures of biology. And in October of 2025, astronomers confirmed a super-Earth less than 20 light-years from our own Sun, practically adjacent by the standards of everything we have discussed tonight. A target close enough that the instruments being built right now could, within the coming decades, tell us whether its atmosphere is holding anything unexpected. This is not a list of hopes. These are active programs with budgets and launch dates and engineering teams and people who have spent careers preparing for what these missions might return. The search is real, and it is happening in the present tense, not some imagined future. And that brings me to the thing I keep returning to, the thought that sits underneath all of this and does not go away regardless of what the data eventually shows. Searching for life beyond Earth is, in a way, a kind of prayer, not to any deity, but to the universe itself, an act of reaching outward with no guarantee of an answer, conducted not because it is required for survival, but because something in us cannot stop doing it. We did not have to build the instruments. We did not have to ask the question. The question does not keep us warm, or fed, or safe. And yet here we are, century after century, pointing our best tools at the darkness and listening as carefully as we know how. We are the species that asks questions it does not have to ask, and we are the species that could not stop looking up. Whatever we find, microbes preserved in the salt of an ancient Martian lake, or complex chemistry in the ocean of Europa, or a biosignature in the spectrum of a world 100 light-years away, or nothing, a silence so complete it forces us to conclude that we are genuinely singular. Whatever the answer turns out to be, it will be the most important discovery in human history, and we will have earned it through the simple, stubborn refusal to stop asking. That is not a small thing about us. That might be the most important thing about us. Go outside sometime soon. Let your eyes adjust. The light arriving from those points in the darkness has traveled years, sometimes thousands of years, to reach your retina in this moment, somewhere in that field of ancient light. Yet the answer is waiting. We are, right now, in the process of finding it, and the night sky will never look the same again. If you enjoyed this deep journey into the science of alien life, please like this video and subscribe to the channel. Your support makes these detailed investigations possible. Tell me in the comments what you think alien life really looks like and where you think we will find it first. Mars, Europa, Enceladus, or somewhere we have not even thought of yet.